In this lecture, we will discuss about problems related to group. So, in previous lecture, we have discussed about the definition of group, and one example we take as for a set of natural number is a example of group or not. But we satisfy only two properties. So, and that means closure property and associative property. Okay, existence of identity is not satisfied and also inverse is not satisfied under addition. So then the set of natural number is under addition is not a group. Now we move to the further. So we can take another example. So another example is let W is equal to 1, 2, 3, 4, 5, and so on is the set of whole numbers set of whole number is a group or not under addition. Under addition. So binary operation we taken as addition. So now we show that the set of whole number is a group or not. Okay. So we take the first property, that is the closure. So for closure property, we know that if A and B belongs to W, so which implies that A plus B also belongs to W. So this property satisfied, you can take any value of A and B from W, so which satisfy A plus B also belongs to W. We can consider as, so let we take any two values that may equal to 1 or b equal to 4. So when we do a plus b, so a plus b, these two value also belongs to W. So we can write down as a 1 plus 4 is equal to 5. 5 is also belongs to W. So here is 5, 6, and so on. So that means closure property satisfied. You can take any of the value. You can take any of the value. Suppose we are taking a equal to 0 and a equal to 0 and b equal to 4. So also satisfy. That means a plus b gives us 0 plus 4 is equal to 4. 4 is also belongs to W. Okay. So closure satisfied. So we write down as the closure property satisfied. Now we move to the further definition. Further definition is related to group is associative property. So second is associative property. So now we move to the next property, that is associative. So associative property. So for associative property, we know that A, B, and C belongs to W. So then A plus B plus C is equal to A plus B plus C under addition. So for this also satisfied, because if associative property is the hereditary property satisfied in each case. So that means we are considering let A is equal to 1, B equal to 2, C equal to 3. You can take any of the value as A, B, C. So we can write down as 1 plus 2. These value belongs to W. So 1 plus 2 plus 3 is equal to 1 plus 2 plus 3. So 1 plus 2, first we solve the bracket. So 3 plus 3 is equal to 1 plus 5. So that means 6 equal to 6. Satisfied. So this property also satisfied. So associative always satisfied. That is the hereditary property. Now we move to the third property. Third property is existence of identity. So this property is existence of identity. So now we move to the existence of identity. In existence of identity, what is the additive identity? Zero. So zero is the additive identity. Zero is the additive identity. Additive identity means under addition, we are taking the operation as under addition. So this is our operation. So when we are performing under addition, so we take the 0 is as additive identity, and when we take the under multiplication, so that means our identity element is 1. So here we see that 0 is belongs to W or not? Yes, so 0 belongs to W. The whole number contain the 0. So we can write down 0, 0 belongs to W. So identity exists. So now we have the property A plus identity is equal to E plus identity is equal to A. So E work as a identity. So that means we can take any value of A. So let we take A equal to 2 and identity E is 0. So that means 2 plus 0 is equal to 0 plus 2 is equal to 2. So this 2 belongs to set of whole number W. So that means identity satisfied. So identity satisfied. So we write down as this property also satisfied. So now three properties satisfied. Now we move to the fourth property, existence of inverse. Existence of inverse. So for proving existence of inverse, so we fourth property is that if A belongs to W, so then minus A. So additive inverse of A is minus A. Minus A also belongs to W. So now we see that when we take A is equal to 1 or A equal to 2, A equal to 3, we can take any value of A which from W. So suppose we are taking A equal to 3. So then the additive inverse. So then the additive inverse of 3 is minus 3. So is minus 3 belongs to W or not? No, because W contain only the positive values. So W contain only the positive values. So minus 3 not belongs to W. So minus 3 not belongs to the W. So that means the inverse. So the additive inverse of any element does not exist. Any element does not exist. That means when we can take 4, the additive inverse of 4 is minus 4. We can take element 5, the additive inverse of 5 is minus 5. So the additive inverse of any element does not exist in W. So that's why W is not a group. So the basic property you can write down as A plus minus A is equal to minus A plus A is equal to 0. Okay. So we can write down that the inverse does not exist. So set of, so hence we can write a set of whole numbers is not a group. Set of whole numbers is not a group. Now, where we have taken two examples. One is related to natural number. Natural number is also not a group because natural number not satisfy the identity and inverse. We can take whole numbers. Whole numbers not satisfy the additive inverse. So this satisfy three properties. Each set of natural numbers satisfy two properties. So now we move to the further. So now next example we can take as uh, the set of integers. The set of integers I is equal to 0, plus minus 1, plus minus 2, plus minus 3, plus minus 4, and so on is a group under addition. So you can remember which set is a group under addition. So set of integer will be a group under addition. We satisfy all four properties. We satisfy all four properties, or we can write down as, so for closure property, first one. So we take the closure property. So let we take A is equal to 1. we take b equal to -1. We can take any two element from I. So these two element belongs to set of integer. Now when we do a plus b, so a plus b means 1 minus 1 is equal to 0. This 0 also belongs to. Now the closure property is satisfied. So when we take any two element from the set of integer, so the set property will satisfied. So that means either you can write down as if A and B both elements be taken from I, so then A plus B is also belongs to I. Now we move to the second property. Second property, that is the associative property. So associative property, we earlier say that this is the hereditary property, always satisfy in each case. Always satisfy, so that means we can take three elements a, b or c which belongs to set of integer I. So now we can write down a plus b plus c is always equal to a plus b plus c. So when we take any element, so that means suppose we are considering a equal to 1 and b equal to 2, c equal to -3. So then a plus b means 1 plus 2 and plus c is -3 is equal to 1 plus and 2 minus 3. So 1 plus 2 is 3, 3 plus -3. So we write down this as, so 1 plus, this is -1. So here we write down as 3 minus 3 equal to 1 minus 1. So 0 is equal to 0. So satisfied. So satisfied. Now we move to the third property. So third property is existence of identity. So existence of identity. So existence of identity. So now we see that that means 0. 0 is the identity. 0 is the additive identity. So now we see that 0 belongs to I. Yes, 0 belongs to I. So then we can write down as a plus 0 is equal to 0 plus a is equal to a. For every a is also belongs to I. So that means when we consider a equal to 3 and e means identity is 0. So that we can write down 3 plus 0 is equal to 0 plus 3 is equal to 3. So identity satisfied in each case. So identity satisfied. So when we add a 0 in any number, so give the same number. So identity satisfied. Now a fourth case we will move to the existence of inverse. In previous two cases, inverse not satisfied. That means neither in natural number nor in whole numbers. Now we move to the existence of inverse. So existence of inverse. So we see that if a belongs to integer, so then additive inverse of a is minus a is also belongs to the integer. So then we can say that a plus minus a is equal to minus a plus a is equal to e. E is equal to means 0. So e means 0, additive identity. So yes, so we can take an example if we are considering a equal to 2. So what is the additive inverse of 2? So additive inverse of 2 is -2. So minus a is equal to -2. So additive inverse of 2 is -2. So you can see that every element have the additive inverse. 1 is -1, 2 is -2, 3 is -3, 4 is -4, 5 is -5, and so on. So every element have the additive inverse. So every element has the inverse, additive inverse. So every element have the additive inverse. So we can write down as a plus minus a is equal to minus a plus a is equal to identity 0. So 2 plus additive inverse of 2 is minus 2 is equal to minus 2 plus 2 is equal to 0. Satisfied. So you can take any value of a from the set of integer I, which always satisfy the inverse. That means every element contain the inverse. Now, so we can say that, so hence set of integer, hence set of integer I under addition, binary operation addition is a group, You have to remember, okay, which set under addition is a group. So set of integer under addition is a group. Now we move to the further means for fifth property, that is the commutative property. That is the commutative property. So when all four properties are satisfied, we move to the further fifth property. So commutative property says that if A and B belongs to I, so then A plus B is equal to B plus A. So commutative is also hereditary property. This also hold in each case. Now let we consider A equal to 2, B equal to 3. You can take any two elements. So we can write down 2 plus 3 is always equal to 3 plus 2. So 5 is equal to 5, satisfied. So you can take any value, any two value from the set of integers and apply in commutative property, so always satisfy. If a commutative property is satisfied, so hence we write down as the set of integer. Hence the set of integer under addition is an abelian group. Is an abelian group. So you remember, so we are taking the problems related to additive. Under additive, so a set of integer is an abelian group which satisfy all five properties of the group. Now, so after understanding the addition, that means binary operation addition, we move to the under multiplication. So you can understand that. So that means we can take an example. We start similarly from set of natural number. Okay, the set of natural number, the set of natural number under multiplication. Under multiplication is a group or not? So under multiplication is a group or not? So set of natural number, we denote it as n, start from 1, 2, 3, 4, 5, generally used for the counting. So is a group or not? So for proving group or not, so that means we satisfy all four properties related to the group, but operation is changed. Earlier we have taken the operation addition, but here we take the operation under multiplication. So under multiplication, so we want to prove that set of natural number, binary operation multiplication. Binary operation multiplication. This is the algebraic structure. You know that this is the algebraic structure. So this structure is a group or not. So we start with the closure property. So when we start the closure property, so closure property says that if A and B belongs to set of natural number, implies that A into B also belongs to natural number. Satisfied? So you can take any two elements from natural number. Suppose we are taking A is equal to 2, B equal to 3. So when we do A into B, so that means 2 into 3 equal to 6, or 6 belongs to the natural number. You can take any two element. So suppose we are considering A equal to 5, B equal to 6. So when we do A into B, so this equal to 5 into 6 is equal to 30. 30 is also belongs to the natural number. So here we, so that means closure satisfies. Closure satisfied. So you can take any two number from n and apply in the closure property, always satisfied. Similarly, we move to the second associative. So associative also satisfied for multiplicative. So for associative, we take three elements. So that means A, B, C belongs to set of natural number. So then we see that A into B into C is equal to A into B into C. So suppose we are considering A is equal to 2, B equal to 4, C equal to 5. So then 2 into 4 into 5 is equal to 2 into 4 into 5. So 2 into 5 4 ja 20. So 5 4 ja 20. So this equal to 2 4 ja 8. 8 into 5. So 8 into 5. So now we see that. So 20, 22 ja 40. So 22 is 40 and 8 5 is 40. So 40 equal to 40. So this also satisfied. This also satisfies. So that means associative property also satisfied. You can take any two, three elements from the natural number and apply. Now we move to the identity. The third property is existence of identity. So you know that under addition, 0 is the additive identity, or under multiplication. So we can write down here also under multiplication. Under multiplication, 1. 1 is the multiplicative identity. 1 is the multiplicative identity. So first we see that 1 is present in the set of natural number or not. So we see that 1 is present in the set of natural number. Here is 1. So identity exists in the natural number. So we write down as 1. Additive multiplicative identity 1. 1 belongs to n. So identity exist. So that means we have the property A into E is equal to E into A is equal to A. So E identity. So here we take A is equal to 4, or E is a multiplicative identity, that is 1. So we can write down 4 into 1 is equal to 1 into 4 equal to 4. So identity is satisfied in each case. So when we multiply any number by 1, so give the same number. So identity satisfied. Now we move to the fourth property. You remember when we are solving the set of natural number for under addition. So under addition satisfy only two properties, that is the closure and associative. Identity not satisfy under addition because identity element is 0. 0 is not belongs to the natural number. So under addition satisfy only two properties, but under multiplication satisfy three properties. Now we move to the fourth property, that is the inverse. So that is the inverse. Fourth property, inverse. So let A, if A belongs to natural number, so then it is necessary A inverse also belongs to the natural number. So that's why we can write down as A into A inverse equal to A inverse into A is equal to E identity. Okay, so A inverse. So A inverse is the multiplicative inverse of A, is multiplicative inverse of A, inverse of A. So here in multiplicative inverse of A is 1 upon A. Multiplicative inverse of A is 1 upon A. So let A is equal to 4. So then the multiplicative inverse of A means A inverse will be 1 by 4. So 1 by 4 belongs to n or not? No. So no fractional number belongs to the natural number. So not belongs to n. So this means that set existence of inverse in set of natural number, existence of inverse is not satisfied for all elements. other than the identity element. So inverse does not exist. Inverse does not exist for each element. So we need the inverse of each element to exist in the same set. So inverse does not exist in each for each element. So hence we can say that n is not a group. N is not a group under multiplication. Under multiplication. Similarly, we do not solve the second part. That means similarly, for example, set of whole number is a group or not under multiplication? No. Set of whole number is also not a group under multiplication because the inverse does not exist. Because inverse does not exist of each element. Another example, set of integers. Set of integers is also not a group. Under addition is a group, but under multiplication is not a group. Under multiplication. Because the inverse does not exist. Multiplicative inverse does not exist. Okay. So now we move to the further example. So prove that set of rational number. Set of rational number. Rational number we denoted as Q, which can be written in the form of P upon Q, where Q is not equal to 0 and P and Q both belongs to the set of integer. Both belongs to the set of integer. Is an abelian group. Under multiplication. Under multiplication. So you remember set of rational number will be abelian group under multiplication. Same, we do the solution. Satisfy the closure property. So that means first we take the closure. So for closure property, let a is equal to 1 by 2. We can take any of the fraction. B equal to 3 by 4. So then a into b. So that means 1 by 2 into 3 by 4 is equal to 3 by 8. B also belongs to Q. These are also belongs to Q. So that means fractional. But Q is not equal to 0. Denominator cannot be 0. We can take any of the fraction which belongs to the set of rational number. Second, associative. Also satisfied. So for associative property, we can take any three numbers. So that means suppose let A equal to 1 by 3, B equal to 2 by 3, and C equal to 3 by 4. So then we do the A into B into C is equal to A into B into C. So A is equal to 1 by 3 into, we write down 2 by 3 into 3 by 4 is equal to 1 by 3 into 2 by 3 into 3 by 4. So first we solve the bracket. So 1 by 3 into 3 to 3 cancels. So 2 by 4 is 1 by 2 equal to this is 2 by 9, 2 by 9 into 3 by 4. Now we solve this. The 1 by 3 into 1 by 2 gives us 1 by 6 and 3 3 is 9 or 2 2 is 4. So that means this also gives us 1 by 6, satisfied. So you can take any three elements from set of rational number, also satisfy the associative property. Third, identity. Identity. So, or also satisfy the identity. Multiplicative identity is 1. 1 belongs to set of number. That means when P equal to 1 or Q equal to 1, so multiplicative identity is 1. So when we take any element, so that means A into 1 is equal to 1 into A is equal to A. So A you can consider as 1 by 5. So we can write down as 1 by 5 into 1 is equal to 1 into 1 by 5 equal to 1 by 5. So satisfied. So you can take any value of A from the set of rational number and multiply by identity. 1 gives the same number. So satisfy the identity. Now fourth is inverse. So in a rational number, inverse also exists. If A belongs to set of rational number, so we can write down then A inverse is also belongs to the rational number. Okay, so we take as A into A inverse is equal to A inverse into A is equal to E. E means 1. So now we consider as suppose A equal to 1 by 2. So A equal to 1 by 2. So what is the A inverse of this? So A inverse of this equal to 1 by 2 to the inverse. This equal to 2. So 2 is also belongs to the rational number. This A belongs to the rational number. So then 2 is also belongs to the rational number. So we can take as P equal to 2 or Q equal to 1. So 2 is also belongs to the rational number. So when we do 1 by 2 into 2 is equal to 2 into 1 by 2. So is equal to 1. So satisfied. So inverse also exists for every element. So inverse also exists for every element. You can take any element. So the inverse exists. So that means, hence we can write down as G, suppose G means a rational number Q. We can write down as, hence Q under multiplication is a group, is a group. Now we move to the fifth property when this is a group. So is this an abelian group or not? So commutative property, commutative property. So also hold. So that means A into B is equal to B into A. So suppose we can consider A equal to 1 by 3 or we consider B equal to 3 by 5. This belongs to the set of rational number. So 1 by 3 into 3 by 5 is always equal to 3 by 5 into 1 by 3. So this gives us 1 by 5. 1 by 5 is equal to 1 by 5. Satisfied. You can take any two element from the set of rational number, put into the properties, always satisfied. So hence set of rational number and set of rational number under set of rational number under multiplication is a abelian group, is an abelian group, is an abelian group.